Okay, let's get started again. Our next speaker will be Athena Chittoor from Carleton College. If you're there.
Yep, I'm here.
So we can hear you, and if you have slides, you can share them.
I will share them now.
Excellent, we can see that. Go ahead.
Nice. Yep. Thank you all for coming to listen to my talk today. I'm going to be talking about investigating the Ki line of M-dwarf stars. So to kind of set the background, one of the ways that we look for exoplanets is that we can look at their Doppler shifts. So we all understand that if a star has an exoplanet, obviously the exoplanet is orbiting the star. But in reality, they're both orbiting their center of mass. And so this causes the star to actually have a very small orbit. And so from our point of view here on Earth, the star will actually move towards and away from us periodically. And because of the Doppler effect, when the star is moving towards us, this causes a blue shift in the light that we see coming from the star, and it sees a red shift when the star is moving away from us. And so we can actually take a look at these red shifts and blue shifts in the spectra of the star. So when we have a blue shift, we'll see it. The spectral lines shift left, and when there's a red shift, we can see these spectral lines shift to the right. So we kind of would expect this to come in a periodic manner. And so if we see something like this in effect, we can kind of say there might be an exoplanet here orbiting this star. But unfortunately, this effect is very small. And is basically obscured by a lot of other effects that can happen on the surface of these stars, most importantly, the magnetic activity on the surface of these stars. So this is actually due to something called the Zeeman effect, in which we can see an excited energy state split into multiple lines. So when this happens, when the Zeeman effect happens because of the presence of amagnetic fields, we'll actually see some sort of effect in the spectral graphs of the star. And so on the bottom left, that is Ki. So you would probably see some sort of widening in the Zeeman effect. You probably wouldn't see a good split, but most of the times you would see some sort of widening or thinning. So we want to take a look at this effect. So in the future, we may say, oh, well, we know that we can kind of expect there to be this periodic change because of the magnetic activity. So we can emit it, so we can more clearly take a look at Doppler shifts. And so when we want to take a look at this, we want to choose a spectral line that's very easy to work with. So thankfully, M-dwarf stars have this particularly strong potassium-1 line in their spectra. We call this Ki. So it's very easy to work with, so we chose this. And so we got all of our data through the Habitable Planet Finder, or HPF telescope. So when we first started, we had a list of about 150 stars, but a lot of the stars did not have enough measurements to work with. So we first had to narrow that down to about 75. And so after that, we had to take a look at the question of how are we going to look at our data. And so the two main ways that we looked at our data were spectral graphs and time series graphs. So on the bottom right is a spectral graph. That's probably what you would think of when you think of looking at the spectra of stars. It just plots wavelength versus the normalized flux. So obviously dips in spectral graphs tell us that there is a presence of a particular element. And so any dips that you see on the bottom right graph, that is the presence of an element, and shaded in green is potassium-1. So obviously very easy to kind of pick out among the rest of the spectrum. And one of the ways that we looked at spectral graphs among our work was that we would layer them on top of each other so that we can more clearly see where there was noise and where there was not. And so the second way that we looked at our data were time series graphs, which plot time, or the date that the measurement was taken, versus the equivalent width of Ki of a particular star. So as you can see on the time series graph, there are large gaps in time, and that's because we are not observing, we're not taking measurements all of the time due to like real world complications. And so we're always going to have some sort of gaps in our data. And also there's some noise that we have to also take account of in our time series. So for measurements that are taken relatively close in time to each other, there's this vertical displacement. And we can say that that's probably approximately equal to our precision when we're looking at the equivalent widths. Of course, the equivalent width being approximately equal to the area of the spectral line. So one of the first things that we set out to do was removing outliers, because the data as we received it, we could not really work with that neatly because there were so many measurements that were just really messing up our calculations. So we needed to remove data points that were obviously extraneous. And so as I mentioned briefly, we need to consider noise, and we have what is called the signal to noise ratio of each measurement of each star. And we wanted to filter out measurements with exceptionally high signal to noise ratios. With being exceptionally high, you have a lot more noise relative to signal. So on the bottom left, the blue measurement, that's very obviously noisy. And so any measurement that we get from that is probably not going to tell us much about the equivalent width. So we may just filter that out. Another thing that we needed to take account of was that, is our data all in line and is everything in place? Because sometimes we would have the wrong bit of data under just each star. So for example, in one star, it actually included measurements from two different stars. So we had to filter that out and make sure that we weren't including two different sets in one data point. Another thing that we had to look at was, is this set of data something that we can actually work with? Because in one case, we were using data points from a binary star system. And in the bottom right, that is those are measurements from that binary star system. Which is very cool, but unfortunately, due to the interference of both of the stars' light, we can't really work with it because the interference is affecting what we see here on Earth. So we can't really take a look at the equivalent width that accurately. So after we kind of went through these 75 stars and we made sure that everything lined up and that every point that we included was a point that we could be reasonably sure was valid, we wanted to kind of take a look at what we had and what we were left with. So one of the first things that we took a look at were how is the data distributed. So we created histograms by just binning certain equivalent width measurements and plotting them as histograms. Of course, we have to also remember that there are large gaps that is going to affect what everything looks like. So we had 75 different histograms, and these are 3 examples of what they kind of looked like. So this would help us kind of figure out which stars we could maybe work with in the future, which stars had the correct placement of data that we kind of wanted to look at the moment. Some other things that we looked at, one of the first being, we took the standard deviation of each star's equivalent width. And we wanted to kind of see if there was any correlation to the standard deviation versus the spectral type of the stars. So as we can see here, each point is a star. And as the spectral type actually increases, there is a slight increase in the standard deviation, which is pretty interesting. And the final thing that we wanted to take a look at was we wanted to double check that the noise wasn't affecting our equivalent width measurements in any way. Because if noise is really affecting our measurements, that'd be pretty bad. And that would mean that we can't really trust the data that we're looking at and the graphs that we plotted. And so thankfully, there was no correlation as the signal to noise ratio goes up, there's no sharp increase or decrease in the equivalent width. So to conclude, one of the ways that we want to look for exoplanets are Doppler shifts in the spectra, but magnetic fields affect the spectra that we see. So we want to account for this. We looked at 75 different stars. We sorted through and removed extraneous measurements so that we can clean up the data to work with. And we tried to take a gauge of what this data looks like through histograms, the signal to noise ratio, and the standard deviation. Now that we're fairly confident that our data is internally consistent, we can actually use this data for future endeavors in finding exoplanets. Yeah, so thank you very much.
Thank you. Let's give her a hand. So time for a few questions, Ben.
Just a question. How did you choose the width of your bins in those histograms? Right. So you could read your histograms, or you could maybe have some justification for choosing the number of bins you had or the widths.
Yes. So we basically chose by how many measurements the star had. So if a star had very few measurements, it wouldn't make sense to have a lot of bins. But if a star had a lot of measurements, it makes sense to put more bins. We tried a few different ways of mathematically making the bin sizes, but those didn't seem to produce any great results. So we did have to kind of eye it from there.
Did you do analysis on any stars that are known to have exoplanets? You had something to check against?
I'm sorry, can you repeat the question?
Did you look at any data from stars that are already known for sure to have exoplanets?
Yes.
You kind of knew what you were looking for.
Yes, because we weren't exactly taking a look at the Doppler shift. We were taking a look at the magnetic field effect. One of the stars that we looked at, TRAPPIST, we are reasonably sure that that star has an exoplanet. And so it was actually pretty good data to work with because we could kind of see this star that we are reasonably sure versus other stars that we are not reasonably sure, and see if there was, so that, we could include both.
Anybody with one more quick question? Okay, seeing none, thanks again, Athena. That was great.
Thank you.